Welcome back. In this video, we're going to cover sections 1.3 and 1.4, and we're going to discuss different types of bonding and various theories to describe bonding and the structures that we observe. So the first question we should be asking ourselves after looking at the atomic structure of various elements is, why do bonds form? And so the general understanding that we use to describe why bonding occurs between the elements is one of stability. Atoms on their own are not very stable, and so the formation of bonds with other elements provides inherent stability over that of atoms. So molecules in general are more stable than the corresponding atoms on their own. Now, there are various types of bonding theories that can be used to describe the structure of organic and inorganic compounds. Thankfully, for organic chem, we can use a fairly introductory theory to describe bonding, and the one that's typically introduced is that of valence bond theory. So in valence bond theory, it's a bonding theory that describes a covalent bond as resulting from the overlap of two atomic orbitals. And so you can see in this image here, we have two atomic orbitals. We have an s orbital and a second s orbital. And we could imagine these representing two individual hydrogen atoms. If we want to form the diatomic hydrogen, H2, we think of this molecule as being the overlap of two 1s orbitals. And so overlapping the 1s orbital of one hydrogen atom with the 1s orbital of a second hydrogen atom results in the formation of a covalent bond. And so when we talk about bonding in this course, we will focus on this orbital overlap. In situations where orbital overlap is quite good, we often refer to that as being a fairly strong bond. But if we consider orbital overlap to be rather poor or not as good, we can consider that covalent bond as being relatively weak. So we're not going to be assigning, for the most part, energy values associated with these bonds, but we generally use this orbital overlap idea to discuss the relative strength of a bond. And we'll look at examples of that in a little bit more detail later on. So here's an example, again, of this diatomic molecular system where we have two atoms overlapping to form what we call a bond, a covalent bond, but typically we refer to this more specifically as a sigma bond. And so all single bonds are often referred to as sigma bonds. And so the electron density of this bond is primarily located around the bond axis. And that's what's trying to be shown here, is that we have the single atom here, another atom to which it's bound to, and we can draw a line between these two to represent that sigma bond. And the overlapping orbitals associated with these two atoms would then overlap in the region of this particular covalent bond, so located around that bond axis. Now, to predict the geometry of a small molecule, that is, the local geometry, or in a sense, the shape of a molecule, we can focus on not only the covalent bonds to which those atoms form with one another, but also the number of non-bonding electron pairs associated with those atomic centers. So if we look at not only the bonding but non-bonding electron pairs associated with an atom, we can describe or predict the general shape or geometry around central atoms. This is really the principle of the valence shell electron pair repulsion theory, or VSEPR theory. And so we know that electron pairs generally repel one another. So electron-electron repulsion is a real thing, and we observe that at the molecular and atomic level. So this repulsion causes electron pairs to arrange themselves in three-dimensional space so as to achieve maximal distance from one another. And so we're going to look at examples now of the different geometries or shapes that small molecules can make when we consider the valence electrons associated with those atomic centers. And specifically, we're going to focus on the number of electron pairs found in bonds, as well as the electron pairs found as non-bonding pairs around those atomic centers. So the first example, here we have the geometrical structure, the structure for methane. Now methane has the molecular formula CH4, so you have a carbon as your central atom, and bound to this carbon we have 4 bonds, 2 neighboring hydrogens. So CH4, and what we see here is this arrangement in which the angles associated with a hydrogen-carbon-hydrogen is 109.5. And this is the same regardless of which 2 hydrogens you use to trace out that particular angle. So this hydrogen-carbon-hydrogen has the same angle of 109.5 as this hydrogen-carbon-hydrogen angle. And we see that in all 4 instances for methane. We give this name, we give this structure a name, this shape a name. We refer to this as tetrahedral. So the tetrahedral arrangement around carbon, as shown in this example, is very typical of carbon atoms that form 4 single sigma bonds to its 4 nearest neighbors. We'll see as we form different types of bonds between carbon and other elements, like pi bonds, that this will also give us different types of shapes. So again, the reason for this is the repulsion between the electrons and the bonding electron pairs between each carbon, or I should say each hydrogen, and the central carbon. So this bonding pair of electrons is trying to place itself in a distance that's furthest away from the other bonding pairs of electrons. And so that gives rise to this tetrahedral shape. Now, if we look to ammonia, which has the molecular formula NH3, it too has a tetrahedral geometry, but there's a distinct difference between ammonia and methane, as we saw in the previous example. In ammonia, there are 3 bonds to the neighboring hydrogen, 3 bonding pairs of electrons, but there's also an orbital around the nitrogen center that contains a non-bonding pair of electrons, shown by these 2 dots. As a result of the presence of this non-bonding pair of electrons, it exerts a greater repulsion between the bonding pairs of electrons than between 2 sets of bonding pairs of electrons. So as a result, the angle between a hydrogen, nitrogen, and hydrogen is actually slightly smaller than what we observed for the methane example. The angle is generally closer to 107 degrees. So as a result, although this is considered a tetrahedral geometry, the geometry of ammonia is often termed not a tetrahedral, but more of a trigonal pyramidal. So trigonal pyramidal is used to describe a situation in which we have a central atom which has 3 bonds that are formed to its nearest neighbors, but 1 orbital that contains a lone pair of electrons. Now, if we look at the example of water, water is also considered to have a roughly tetrahedral geometry. However, similar to what we saw for ammonia, water has two lone pairs around the oxygen center. And again, because these lone pairs repel other bonds more strongly, the HOH angle is even smaller than what we observed for ammonia. The angle is closer to 105 degrees, and so the geometry that we typically refer to for water is that of bent. So in these three examples, we have slightly different terms to describe this geometrical arrangement. We have tetrahedral for angles that are close to 109.5. We have trigonal pyramidal for situations in which the angle is closer to 107. And then finally, we have bent for situations in which the angle is closer to 105. And these are specific examples, of course, for methane, ammonia, and water, but we see these angles in larger structures as well. Now, if we look at a situation in which we only have 3 pairs of electrons, in this example, boron trifluoride, we have 3 bonding pairs, each pair forming a covalent bond between the boron, the central boron atom, and a fluorine atom. In this particular situation, we have 3 bonds, and the best way to distribute those bonds in 3-dimensional space so that they minimize their interaction, minimize their repulsion with one another, is to place them at 120-degree angles with respect to one another. So in boron trifluoride, we have a fluorine-boron-fluorine bond angle of 120 degrees, and we see that repeated between the other fluorines in that structure. This structure, as you can see, is going to be considered planar. It's quite flat. It sits on our screen, and so the name we give to this particular structure, this geometry, is trigonal planar. And we will see this for other systems that contain what's known as an sp2 hybridized center. We'll get into those details a little bit later, but this trigonal planar geometry typically see with carbonyl containing compounds. The carbon double bond oxygen has an sp2 hybridized structure, so those regions of a molecule have a plane or have that flatness associated with them. And so the last example of geometries that we can somewhat predict for small molecules using the valence shell electron pair repulsion theory is shown here, where we have, in the case of beryllium hydride, BeH2, we see this linear geometry. And this arises from the fact that beryllium can only form 2 bonds to 2 other elements. And so therefore, we have 2 bonding pairs of electrons. And so the easiest way, or the best way to arrange these 2 bonding pairs of electrons in space, such that they minimize their repulsion with one another, is to place them in this fashion, where they're 180 degrees apart from one another. So that gives rise to a geometry which we refer to as linear, that the angle between this hydrogen, beryllium hydrogen, is 180 degrees. We see this similar geometry when we look at molecules like CO2. Now CO2, the carbon and oxygens in CO2 aren't forming only sigma bonds. We have pi bonds associated between the oxygen and carbon, but the overall angle that we observe between the oxygen, carbon, and oxygen is also 180 degrees. And so this too is considered to have a linear geometry. So we'll look at other examples of how the valence shell electron pair repulsion theory allows us to better describe the shape that we observe between groups of atoms in various molecules, or just in general for the shapes of small molecules. So that concludes this video. If you have any questions about what was covered in sections 1.3 or 1.4, please email me or start a discussion in our forum in UR courses. Thank you.